Hello, Garrison.
You-
How are you doing today? So what kind of math? Can you hear me? Sounds like we might have an audio problem. Did you unmute your microphone? Not hearing anything. Can you call me on the phone if you're hearing me?
Can you hear me?
Yeah. Let me hang my phone up. I was just calling you. You still there, Garrison?
The audio was connecting.
Okay. So you can hear me okay?
Yes, sir, I can hear you. I'm trying to make sure that the mic is adjusted properly.
Yeah, I can hear you fine.
Okay.
Okay, so what are we doing today?
All right, some more trigonometry functions. We learned some new formulas.
Okay.
So some of them were like what you had said with the negative angle identities, like the sine of negative x is equal to the negative sine of x.
Yeah.
And then some of them were the product to sum formulas, like the sine of u times the sine of v is equal to half the cosine of u minus v minus the cosine of u plus v. So,
Yeah, those are just algebraic manipulations of the basic identities. I think,
the basic idea.
yeah, I think what you want to do is learn the basic identities. In other words, learn what this is and learn what this is. And once you have both of these down, that covers pretty much everything. Everything else can be derived from that. I'm not talking about half angles and double angles. In other words, you also need to know what that is, and you also need to know what these are.
Yes, sir.
So those are your basic identities, and not just cosine, but sine or cosine. In other words, memorize these four.
Those four.
Those,
all right.
because tangent is sine over cosine, so you can figure out tangent. Now, it might be worth memorizing tangent. It depends on how many problems they give you that have tangent. Tangents, I'm not sure I have it memorized, but I know I can figure it out because it's sine over cosine.
Yes, sir.
So specifically, what problems do you have?
Yes, sir. We have, all right. The first problem is the cosine of 285 degrees times the sine of 15 degrees, and it's asking to evaluate.
Okay. Without your calculator, correct?
Without the calculator.
Okay. So we've got a number of choices here. In other words, what we know are sine and cosine of 30, 45, 60, and 90, right?
Yes, sir.
And multiples of those we can always figure out.
Yes, sir.
So we're going to use our identities. And first of all, let's figure out what the best way to talk about that is. It's obviously not double angle because we don't know what 142.5 degrees is.
Yes, sir.
could be half angle. That would be 570, which is 190. That's not one that we know.
Is there a way to go product to sum or sum to product?
Well, that's a part of trig that I rarely get. I don't have those memorized. I would continue to look for, you may be on the right track, I don't know. But in terms of that angle right there, is that anything that we know? In other words, excuse me, we know what the common angles is going to be a 135, so that's 135 plus 150. We know those two.
Yes, sir.
In other words, if I'm able to split it up, because that is 90 plus 45.
Yes, sir.
This is 90 plus 60. The key is we know what 45 and we know what 60 are.
Yes, sir.
So let's plan on representing this cosine function as the cosine of 135 plus 150. So let's start there. And the sine of 15 degrees could be the sine of 30 divided by 2.
Yes, sir.
And this answer, your half angle formulas, all come out to be sines and cosines of that angle. So
Yes, sir.
that's not a bad plan. So let's go from there. I mean, I don't think we need to do product to sum yet. There's no need to invoke that. If you don't have to go there, don't go there.
Yes, sir.
At this point, we have figured out how to split up 285 into two angles we know. And we figured out how to do sine of 15 degrees. And there's a couple of choices there. We could also say the sine of 45 minus 30. Let's do it just to be consistent. In other words, we're going to work on the sum and difference formulas this go around. See what I'm doing?
Yes, sir.
All right. So what's the first one? Well, first of all, what's the general formula? In other words, what's the cosine of A plus or minus B equal to?
Cosine of A times cosine of B minus or plus sine of A times sine of B.
All right. Cool. Just fill it in. So it's cosine of what?
So cosine of 135 times the cosine of 150 minus the sine of 135 times the sine of 150.
Fill in all those. Tell me what the cosine of 135 is.
That is negative root 2 over 2.
It's cosine of 150.
So that is negative root 3 over 2.
Safest to use parentheses for all of these.
Yes, sir.
I mean, I almost didn't do it, and I could have gotten myself in trouble by not doing it. Okay, what's the sine of 5 degrees?
Root 2 over 2.
Positive. And
Positive.
what's the sine of, what is that, 150?
150. So that's 1/2.
Okay. And now we can, here, let me do this. Simplify this. The cosine part.
Yes, sir. Root 6 minus root 2 over 4.
Remember I said that's a common answer?
Yes, sir.
Well, you're going to see it a lot. It truly is a common answer despite its strangeness. Root 6 minus root 2 over 4 is a very common answer. Because they're always dealing with these angles that it's root 2 over 2, or it's root 3 over 2, or it's 1 over 2.
Yes, sir.
And then, what's this part of it?
Oh, I already.
Whole answer. No, oh yeah, you were giving me the whole answer. Okay, and that's correct. You just skipped ahead a little bit. Okay, now let's do the sine.
Yes, sir. So that is the sine of 45 times the cosine of 30 plus the sine of 30 times the cosine of 45.
Fill everything in.
Yes, sir.
Sine of 45.
Root 2 over 2.
Cosine of 30.
That is root 3 over 2.
Plus sine of 30.
Run half.
Cosine of 45.
Root 2 over 2.
Okay. So, what does that simplify to? Root 6 over 4 plus root 2 over 4. So it's root 6 times root 2. Oh, hold on. What did I do here? Let's see. It's root 6 plus root 2 all over 4. Correct?
I think so, but
That's
hold
root
on.
6 over 4. That's root 2 over 4. Add them together, you get root 6 plus root 2 over 4. And then the only reason I multiplied here, because that's the original problem. In other words, I've skipped kind of a step because I ran out of room.
Wait a minute. I realized that messed up. It is the sine of 45 times the cosine of 30 minus the sine of 30 times the cosine of 30.
Right. You are right. I messed up not catching that. Sine is the same. Cosine is opposite. So this is going to be minus instead of plus. So now our answer, make a little bit of room. Don't need that. Ooh. Actually would have been better if it was plus, because it would have turned everything into whole numbers. Basically, what we have is minus that not squared, but times, what am I doing here? Same thing. That should be your answer.
Yes, sir.
Now, I can do the algebra, but we're still going to be left with a square root of 12 in the middle. So
Yes, sir.
we're never getting rid of the radical sign. We can simplify it. Do you have answers on these?
No, sir, I do not. But that looks right.
Yeah, this would, if you had like a multiple choice test, this might be the answer you'd be looking at.
Yes, sir.
I suppose if I were to multiply it together, I would get 6 minus 2 root 12 plus 2 all over 4. So
It'd be over 16.
over 16, excuse me. So that's 8 minus 2 root 2. Hold on, let's just keep taking this down, which is usually the way you want to do it. So it's 8 minus 2 root 12 all over 16. I divide top and bottom by 2. I get 4 minus root 12 all over 8. Now I can pull a 2 out of that. So it's 4 minus 2 root 3 all over 8. Now I can divide top and bottom by 2 again.
Yes, sir.
So it looks like this would be a final answer, although I wouldn't bet my life on it just because we've done so much arithmetic, it's easy to make a mistake.
Yes, sir.
But this could easily also be, if it was a multiple choice test, that would be an answer, and if it's not a multiple choice test, this would be the answer you'd want to give.
Yes, sir.
As opposed to this one over here. That's just not simplified enough. Could be an answer on a multiple choice, but like I said, if you have to give them an outright answer, it's this one. And you don't convert it to decimal. Unless they specifically say round it off to, like the nearest hundredths or something. You leave it in radical format. That's the exact answer.
Yes, sir.
All right. What other problem do you have? That's
Okay.
a pretty good one. Now, we used sum and difference formula only for that. I could have used the double angle or the half angle formula for the sine of 15.
Yes,
And
sir.
I would have gotten the same answer, but the numbers wouldn't have been quite the same as we saw last time. Some of these answers can look a lot different, but be exactly the same.
Yes, sir.
All right, what else you got?
All right.
Incidentally, it is easier in degrees than it is in radians. Had that, whatever number it was, 285 degrees, had that been in radians, I would have converted it to degrees merely because it's easy to figure out, what two angles add together when it's in degrees. You know what degree angles, you know which one of those and which ones you'd have to use a calculator on. So whenever you're doing these kind of problems, it probably makes sense, even if they give it to you in radians, to convert it to degree.
Yes, sir.
All right, what do you got?
Okay. So the cotangent of theta is equal to...
I'm sorry, cotangent of what?
Cotangent of theta.
Of theta, okay.
We use theta a lot.
That's fine. Just like x, no difference. It's an angle. We always take trig functions of angles.
Yes, sir. So the cotangent of theta is equal to -3/4, and theta is in quadrant 2. And what this is asking is use the given information to find the sine, cosine, and tangent of 2 theta.
Okay. In order to find the sine, cosine, and tangent of 2 theta, we need to figure out what the sine, cosine, and tangent of theta is.
Yes, sir.
Because all of those formulas are based on sine of theta, cosine of theta, and tangent of theta.
Yes, sir.
So let's start. You know what? I'm going to do this the way I tell everybody to do it. This is probably the most common question in Trig.
Yes, sir.
Seriously. Where they give you one trig function, they give you its value, and they tell you which quadrant it's in. There's always a beginning first step that I want to take. What is it? Always on this prototypical question in Trig. Somebody was testing you and they could only ask you one trig question, this might be it, or something similar to this. And there's a first step.
Find its inverse.
No, draw a right triangle.
Draw a right, okay.
That's
draw a right triangle.
the first step. And label it. It's got to be a right triangle. And you got to label where theta is. I usually put theta down there, but it doesn't have to be down there. It could be at the top.
Yes, sir.
Okay. Now, I have enough information to label two of those three sides.
Yes, sir.
What are they? Which ones can I label? By labeling, I mean put a dimension on it. Based on the fact that that is true.
Yes, sir. The side opposite theta is 4, and the side adjacent to theta is 3.
That would be if it were the tangent of theta. Cotangent is the reciprocal of that. So it must be that and that. Is that what you gave it to me the other way, didn't you?
No, I said opposite was 4.
Opposite is 4. So, ka, toa. Tangent is opposite over adjacent. This is not tangent, it's cotangent. So it's going to be the reciprocal of that. Cotangent must be adjacent over opposite, which is the way I've labeled it. Right?
Yes, sir.
Okay. So, once you've labeled two sides of that triangle, you can always label the third just using the Pythagorean theorem. And notice that I did not put any negative signs. When I'm drawing a triangle and dimensioning it, I don't use the negative sign. The negative sign merely points me to the fact that we know theta is in the second quadrant. Cotangent's always negative in the second quadrant. Okay? So when you do this first step of drawing a triangle, do not worry about that negative sign. What's the hypotenuse?
5.
Okay. Now you can give every single trig function of theta. Let's just write them all out. Because all of our double angles and all of our whatever else they wanted to use, half angles, they're all functions of these three functions. I don't even need to write the rest of them out. Tell me what sine of theta is.
4 over 3. No, 4 over 5.
Okay.
I read what I wrote wrong.
4 over 5. Okay. What's cosine of theta?
Negative 3 over 5.
Okay. Because it's in the second quadrant. And what's tangent of theta?
Negative 4 over 3.
All right. Now, question said what?
Find the sine, cosine, and tangent of 2 theta.
Sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. What's the formula for the sine of 2 theta? What's the general?
Sine of 2 theta is 2 times the sine of theta times the cosine of theta.
Fill everything in. Notice we know what the sine of theta is and the cosine of theta.
Yes, sir.
So fill them all in. What goes here in the first parentheses?
4/5
goes in the second.
Negative 3/5.
What's that answer?
So that is negative 24 over 25.
That's what the sine of 2 theta is.
Yes, sir.
Now, the cosine of 2 theta is a bit unique. It has 3 different identities. And there's a reason for that. It's from calculus. all three of those identities become extremely valuable when you're doing calculus. But in trig, it's just kind of an oddity. In other words, it's cosine squared of theta minus the sine squared of theta. It's also equal to 2 sine squared of theta minus 1. And it's also equal to 1 minus 2 cosine squared of theta.
Do you have those last two?
I got them backwards?
Is it one minus 2 sine squared of theta?
I don't know. I might have it backwards. Let me look it up. If you have the table, go ahead and tell me.
I think it's 1 minus 2 sine squared theta. Okay. That's what I have.
Okay. If that's what you've got in a book, that's what it is. I apologize. Let me erase these. Fact, I'm not going to use those two because I don't need them. I know what cosine of theta is, so I know what cosine squared of theta is. I know what sine of theta is, that means I know what sine squared of theta is. Let's just use that one. That one I can always remember. I'm never wrong on that one. The other two I tend to get mixed up sometimes. So,
yes,
if you're not positive of those other two, then use the one you're positive of. What's cosine squared of theta?
9 over 25.
What's sine squared of theta?
Negative 16 over 16 over 25.
Yeah, be careful here with putting a negative sign in front of it, because that can get you the wrong answer. In other words, I knew subtraction was happening right there, so I already wrote the negative sign. Okay, so that is negative 7 over 25. So that should be the answer for cosine of 2 theta. And if you think about it, if theta is in the second quadrant, cosine of theta could be in the third quadrant. Also could be in the fourth. You don't know. But ending up with a negative sign on it tells me it's in the third. Ooh. Remember, that's cosine of 2 theta. It's not the cosine of theta. It's cosine of 2 theta. So
okay,
yes, with a negative sign. We know that theta is in the second quadrant. We just don't know where 2 theta is. Second quadrant could be 91 degrees. So 2 theta could be 182 degrees, which is the third quadrant. Second quadrant could also be 179 degrees. So 2 theta could be in the fourth quadrant.
Yes, sir.
Knowing that theta is in the second doesn't really tell us where cosine of 2 theta or where 2 theta is.
Yes, sir.
But this kind of does. It's not in the fourth. Cosine of 2 theta is in the third. Okay. And then the last thing they wanted was the tangent of 2 theta.
Yes, sir.
Let me see if I can remember this. This is kind of hard to remember. I'm trying to remember it. I want to say divided by 1 minus tangent. No, that's the plus and minus. What is it? I don't remember it.
The tangent of theta?
Yeah, what's the tangent of 2 theta? What's that idea?
Tangent of 2 theta. I think it is 2 tangent of theta minus tangent squared theta. Over 1 minus tangent squared.
1 minus tangent squared of theta. I knew it was a ratio.
Sorry about that.
Okay. And then we know all of those. So let's stick numbers in. In other words, we know what tangent of theta is. So it's 2 times what?
Negative 4 over 3.
Divided by 1 minus
16 over 9.
So that gives us minus 8/3 in the numerator. In the denominator, it gives us minus 7/9. How do we solve that?
multiply it by the reciprocal of the denominator.
Okay.
Or simplified, it is.
Yeah, so it's basically 8/3 times 9/7, right?
Yes, sir.
Negative signs cancel out. So this becomes 24/7.
Yes, sir.
That's the answer to that right there.
Yes, sir.
Let me think about that for a second. We know it's in the third quadrant, the tangent of 2 theta, because the cosine of 2 theta told us it was in the third quadrant. So we know
Yes,
that 2 theta is a third quadrant angle. Well, tangent's
yes,
supposed to be positive in the third quadrant, and it is. So in other words, there's no glaring red flags that are contradicting anything.
yes, sir.
And it's always useful in math to apply a ballpark test like that. In other words, make sure your signs all come out where they're supposed to be.
Yes, sir.
All right. It's too bad you don't have answers on any of these.
No, sir, I don't have answers, but
I'm fairly confident of these answers, but it's always nice to have the answer just to verify that, we didn't make a mistake in our math or we didn't make a mistake in our formula. That's a pretty big one you want to memorize right there, what the sine of 2 theta is. Only because the sine of 2 theta only has one identity.
yes, sir.
Cosine of 2 theta has 3 of them. And you got to get those last 2 in the right order, which I screwed up. So it's easy to get cosine of 2 theta off. And then the tangent of 2 theta, it's not that hard to memorize if you kind of think of the top as being 2 tangent of theta and then the bottom as being what it is. I don't know. The tricks you use to memorize stuff in Trig, it's kind of different for everybody. So I'll let you kind of worry about how to memorize some of that stuff.
Yes, sir.
All right, what else do we got?
Okay, so we just recently learned about the sums and differences of sine and cosine functions.
Okay.
And it seemed a bit odd to me, so maybe we can work out
You talking about sum and difference or product to sum?
a sum of sines and cosines.
Okay, that's what we've been working with. That was the first problem we did was all about that. That's the only thing we used.
Well, what it describes is if a sine function and a cosine function have real coefficients and the same period, they can be added or subtracted and written as a single sine or cosine function.
Okay.
So, is that...
Sounds like you... Can you give me an example?
All right. Negative 3.
I'm sorry, what?
Negative root 3.
Okay.
Sine of x plus the cosine of x. And we have to write that expression in terms of sine only.
Okay. Well, the key identity between sine and cosine, if they're not squared, is this one. It's the cofunction identity. And it applies to sine and its cofunction cosine. Also applies to tangent and its cofunction cotangent. And it also applies to secant and its cofunction cosecant. And goes the other way also.
Yes, sir.
So, all I have to do is write one of these in terms of the other one using either of those identities. So let's use that one and rewrite this thing.
Yes, sir.
Plus what?
Plus the sine of 90 minus x.
Yeah. And that was the instructions, right? Just write it all in terms of sine?
Write the expression in terms of sine only.
Yeah, that's what we've done. Now, these are very important if you're just dealing with sine and cosine. What you are frequently dealing with is sine squared or cosine squared. Then the key identity is this one. There are 11 identities that you just absolutely got to memorize. And this is probably the most important one. In other words, you won't run into sine squared x plus cosine squared x. What you'll run into is 1 minus cosine squared x. What do you replace that with? Sine squared x.
Yes, sir.
So when everything's being squared, you use this identity. When nothing is being squared, you use one of these two.
Okay.
And in this case, nothing's being squared. It's not even an equation, it's just an expression. They just wanted you to rewrite the expression in terms of sine. We've done that. And now notice that we could actually use the sum and difference formula for that part of it.
Yes, sir.
We could take it down a little bit, simplify it perhaps. Oh no, but the sum and difference formula would bring in sines and cosines. Although I do believe that the cosines, I don't know. Yeah, I think this got to be the answer. In other words, you wouldn't want to use the sum and difference formula because all of a sudden you reintroduce the cosine.
Yes, sir.
So we've accomplished what they asked. That should be a final answer.
Yes, sir.
Okay, what else?
Let me give you an example. Let me give you an example of something that they said.
Okay.
To write two functions as a single new function.
Okay.
They say that a times the sine of bx plus b cosine of bx equals k cosine of bx minus the angle or theta. And bx minus theta is in parentheses. bx plus theta.
X should be theta, so they should be the same thing, right?
I think so.
Yeah, in other words, if I say the sine of x, x is clearly an angle. Because I can't take trig functions of anything but angles. Okay.
Yes, sir.
And x is also theta. So did I write that right, or are there parentheses involved on the right side?
Bx plus x is in parentheses.
So it's like this.
Yes, sir.
All right. And what do they want you to do with this?
Combine two functions into a single function, into a single sine or cosine function.
Well, looks like they did it. Okay, so that's what they've done.
That's the example. Now, a problem that they have for us to combine is by using that is y is equal to 1/2 the sine of x plus root 3 over 2 the cosine of x. And it says that since they have the same period, x, since their b is the same, we can combine them.
Yeah, okay. So as long as they are giving us that, this sounds like sum to product.
Is this sum to product?
Well, I think it is, because we have a sum on the left side of the equation, and we have a product on the right side. So let me just pull up my formulas for that. Sum to product, yeah, 505. We don't really need any more than what you've given me. because what you gave me was A, B. So let's list it. A is what?
Oh. A is 1/2.
Oh, I see what the problem's going to be. What's B?
√3/2.
No. Oh.
Oh, capital B is √3/2.
What did I write wrong in this thing?
Well, the lowercase b would be 1 for both of them.
Okay. So lowercase b is 1. Although, right here, that indicates lowercase b is square root of 3/2. Is this supposed to be something other than lowercase b?
The A and B are both supposed to be uppercased.
So the b's aren't the same.
They are not the same.
Okay. And yet we do have a k on the right side also, correct?
Yes, sir. And they've given that k is equal to the square root of a squared plus b squared. So sort of like Pythagorean theorem.
Yeah. And it's the capital A and B, right?
Yes, sir.
Okay. So little b is 1.
Little b is 1 for both of them.
And this is capital A, this is capital B, there's little, see, capital B is square root of 3/2, correct?
Yes, sir.
Little b is 1.
Little b is 1.
And k is square root of 1/2 squared plus square root of 3/2 squared. Well, that's square root of 1/4 plus 3/4 square root of 1. So k is 1.
K equals 1. They've given two more things. That the cosine of theta is equal to A over basically the value of k, and that the sine of theta is equal to B over k.
Okay. I'm not sure why we need that. It almost feels to me like this is all the information we need right over here. In other words, that is enough to write the right side of that equation, is it not?
Let me
In other words,
see.
the left side of the equation is this right here, without the k in it. Right?
Oh, I think I know.
Match that up to this.
Okay, I think I realized what it is. The farthest x that you have on the top equation, where you have cosine of bx plus x, that farthest x is supposed to be a theta, as in, like, it's a completely separate value.
Oh,
and
that's the phase shift part of it.
That's what it is.
The phase shift part of it. Yeah, that's usually called C. In other words, in your sinusoid functions, that's called C, yeah. Although, that's a whole nother topic that have we covered sinusoid functions? I don't think so. They come after all this other stuff. So anyway, do we still have enough information? In other words, so what do we have? K is 1.
K is equal to 1, so that is...
Sine of B is, little b is 1. And that was supposed to be little b in front of the x?
That's right, yes sir. 1 cosine
theta. Isn't that the answer?
Plus theta. Okay, and they wanted the A over k and B over k to be used to find theta.
Okay.
So...
Okay, I can figure out what we're going to do here. That is the sum, right, that we're going to use?
The sum?
Well, we're looking at a sum of two angles, x plus theta.
x plus theta.
So that would be the cosine. See, the sum for cosine is cosine cosine minus sine sine. And now we know what the, do we know what the cosine of x is, or is the cosine of theta?
Oh,
These identities over here on the right side. Is that x or theta?
theta.
That's
Theta.
Okay. So what we have is cosine of x. Cosine of theta is a over k, right?
Oh, that's those are only for finding theta. Oh, cosine of x times a over k. Okay. That's right.
Okay, minus sine of x. And what's the sine of theta?
B over k.
Unfortunately, we still have a difference now.
I think they wanted something like, since we know a and k, we plug those in to the formulas on the right, where a would be 1, k is 1. So if the cosine of theta is 1/2, that would make it a 30-degree angle. And we would have cosine of...
Oh, I see. Because you know a and k, so you can figure out theta.
Yes, sir.
Okay, let's do it that way. So let me go backwards here. So cosine of theta equals 1/2 divided by 1. Is that correct?
Yes, sir.
Which is 1/2. Which means we know theta is 60 degrees.
Yes, sir.
So theta is 60 degrees. And now can we just use that?
Wait, if was the cosine...
The second part of it. Because all we need is to figure out what theta was. And we just figured it out by knowing that it was a over k. Not sure we know which quadrant it's in. But if I use that as the answer, then your final answer is going to be k, which is 1, times the cosine of capital B, or little b, which is 1, plus 60 degrees. Is that an answer that looks like it would be correct?
I think if it would be x plus 60, it would be sine of that. Because
why sine of that? That says cosine.
they've described that, well, instead of cosine x plus 60, it would be sine x plus 60, because they say that when you're trying to find the combined sine of the functions, the cosine is equal to a over k. But when you're trying to find the cosine of the combined functions, the sine is equal to a over k.
Oh. Okay, so these aren't the way I've written them then.
I think you wrote them for the sine. You wrote them for the sine. I think that's what it is.
Okay, and yet we need it for the cosine, because the general formula is equal to k cosine, correct?
If it were cosine, maybe I just said this wrong. If it were cosine, it would be bx minus theta. I think that's what it is. It just...
Oh, that's because sine is equal to cosine of 90 degrees minus theta. Perhaps is where the confusion is coming in. In other words, if what the cosine of x plus 60 is, remember that I know, here, let me make some room over here. I always know that sine is cosine of 90 minus theta. So the cosine, I don't know if I've got this right or not, but that's going to be equal to sine of 90 minus all of that, x plus 60, which ends up being the sine of 30 minus x. Here, I'm staring at some equations here that are sum and difference. I'm sorry, product to sum and sum to product. Does this sound familiar?
It sounds familiar, but...
Let me just write one out. And this sounds like it is a sum to product. The only thing is, I don't have one to cover sine plus cosine. All the ones in my book are sine of theta plus, or sine of alpha plus sine of beta, or sine of alpha minus sine of beta, or cosine alpha plus or cosine minus. So I don't have one that does these two. This is probably the first time I've seen this formula that I can think of. It's probably derived, but you just rewrite it. I got it awfully messy here. And tell me if I'm writing it properly. So is that an identity?
It should be bx minus theta.
That's the problem, I think, in what our previous answer was. Okay. Now, we also know what? About cosine of theta and sine of theta.
They are part of the...
Well, what's it equal to in terms of A, B, and K?
Oh, okay. So for this one, I want to make sure I don't mess this up because I've got two different equations. So the cosine of theta would be b over k.
Capital B or little b?
Capital B over k.
Okay. Which means we know what capital B and K are for our problem, so we can figure out what theta is.
Yes, sir. So cosine would be root 3 over 2. Cosine of theta would be root 3 over 2.
I thought capital B was root 3 over 2?
Yes, sir. Capital B was root 3 over 2 and K was 1.
Is what angle?
Theta is 30.
Okay. Now, I believe we have everything, don't we? In other words,
yes,
we know A is what I've erased the one you were supposed to, or that we're trying to.
A is one. Capital A is 1/2.
Okay, and capital B is what?
Is root 3.
Root 3 over 2, and little b is 1, and capital K is 1, correct?
Yes, sir.
How do we know capital K is 1?
Because it said that
there was no coefficient in front of the right side, right?
Yes, sir.
Okay.
K is equal to the
right
square root
So here's what we are looking at. We have 1/2 sine of little b x, which is that, plus √3/2 cosine of x. The question is, what is that equal to in terms of that?
Yes, sir.
Well, k is 1.
That's right.
Cosine, little b is 1.
X.
What theta is. So erase that 1. That should be our answer.
I think that is.
Now, that also happens to be the sine of 90 degrees minus that angle. In other words, 90 degree minus that angle, which is x minus 30.
Oh.
So if I want to answer this with sine, it's the sine of 120 degrees minus x.
So it's the sine of 100. Oh.
Or it's the cosine of x minus 30, and I frankly prefer this answer because it's a smaller angle, first of all. You don't want to use second quadrant angles if you can use first quadrant angles. And secondly, this is x minus 30 as opposed to 120 minus x. So it's a little easier to work with that one as an answer. But it's also the obvious answer because the general formula they gave you, the right side of the equation is cosine. It's not sine.
Yes, sir.
So I would think this would be the answer they're looking for.
Yes, sir. I think it is.
Okay, good. Yeah, as long as they give you this, then you're fine. It's interesting that, yeah, oddly enough, in my chapter on sum to product and product to sum, which very few students cover, they just don't get to it. It's not part of the common core. But clearly this is sum, right? That's a sum of something. Now, I guess that's the product of something, k times.
I think in the sum and product, they always have the product of two different.
Yes, well, they always have the sum of the same thing, or the difference. In other words, this is sine, that should be sine. Or if this is cosine, that should be cosine. So I don't actually have a formula for the sum to product if you're using different trig functions. Probably could come up with one by using this sine equals cosine of 90 degrees minus x. You can always use that one.
Yes, sir.
But I don't see a need to do it here. And in fact, we don't need to look for formulas for sum to product. They've given you the formula. I don't know where they got it from. I'm not sure I've seen it before. But as long as this is true, then it's easy enough to solve the problem they gave you.
Yes, sir.
Only because we can figure out what capital A, capital B, little b, and capital K are, and theta.
Yes, sir. Yes, that's right.
I wouldn't worry too much about product to sum and sum to product unless they specifically give you problems about it. This formula is probably derived from sum to product, is my guess. That formula at the top that they gave you?
Yes, sir.
I wouldn't doubt that that came from sum to product and then a lot of algebraic manipulation.
Okay. I mean, maybe.
As long as they give you this, then you're fine. because in the formula they gave you, you're able to figure out what capital A, capital B, little b, and capital K and theta are.
Yes, sir. That's right. I mean, they didn't show the, they didn't really show the proof of the formula.
No, we're just
And
that's a correct formula, and I'm sure it is.
that, I mean, that's what had mainly concerned me. I had just seen the formula and I had wondered where did they get this, because I didn't really think it was a sum or product, because each of those you would always have
Right.
two different trigonometric values, but here you're working with different functions.
My guess is they've taken that part of it, this part right here, and changed that to cosine of 90 degrees minus bx.
Yes, sir.
And then you would have cosine there, and you could use their sum to product formula.
Yes,
Which I don't have memorized because, like I said, it's only about once every 4 years that I get a student that covers sum to product. Most do not even full trig students.
Really?
Yeah, you can take a full semester of trig, nothing but trig, and not cover sum to product or product to sum.
Yes, sir.
All right. You good to go, Garrison?
Yes, sir. I think so.
Okay. Good luck.
All right.
You have a good evening. I'll talk to you next time. I'll talk to you Thursday.
Yes, sir. Have a good evening.
You too. Bye-bye.
All right.